Hello, everybody. Hi, everybody. I hope you can hear me. So I guess it's time to start. So today I'd like to talk, well, first of all, I hope that you're well wherever you are. And today I'd like to talk more about acyl substitution. So that's what I want to talk about today. And then Friday's discussion, I guess, eventually that exam number 2 will happen eventually. And I guess on Friday, we can review for the exam. But today I'd like to talk about acyl substitution, which is what's going on in the lecture now. All right, so last time we started introducing the topic of acyl substitution, and the thing you really want to focus on is, remember, you're looking for a carbonyl carbon. Acyl substitution is a reaction that happens with carbonyl compounds where the carbonyl carbon is bonded to something that is not carbon and not hydrogen. So I'm calling this thing Z. What can Z be? It can be oxygen, it can be nitrogen, it can be sulfur, it can be halogen, it can be a lot of things, just not more carbon and not more hydrogen. So something that's not carbon and hydrogen on one side of the carbonyl carbon. Acyl substitution can happen under acidic, neutral, or basic conditions. But whatever the conditions are, the end result will be whatever this group is that is not carbon and not hydrogen. That is going to go away, and its place will be taken by the nucleophile. So in acid conditions, the nucleophile enters with its nucleophilic atom protonated, and so put H plus over the arrow to show its acidic conditions. And what happens in acyl substitution is the thing that's not carbon and not hydrogen, that's going to break off. The nucleophile is going to take its place minus the proton that the nucleophilic atom rides into town with. So under acidic conditions, the product here is going to be, all right, that Z group is gone. The Z group is gone, and the nucleophile has taken the place of the Z group minus the proton. And where did that proton end up? In a formal sense, it departs with the Z group, which is which functions effectively as a leaving group. Okay, so a concrete example of this reaction, acyl substitution basic conditions, would be something like, okay, there's the acyl derivative. It's a carbonyl carbon. It's bonded to something. It's not carbon and not hydrogen. Now let's bring in the nucleophile. The nucleophile could be this tertiary amine. Sorry, the secondary amine. So the nitrogen, that's the nucleophilic atom. It's under acidic conditions, so the nucleophile is entering with a proton on the nucleophilic atom. The thing that's not carbon and not hydrogen, that's going to break off, and the nucleophile minus a proton is going to take its place. So in this concrete example of acyl substitution, we see this is a way of going from an ester to an amide. All right, so that's the overall reaction, the net reaction, the predict the product kind of problem of acyl substitution under acidic conditions. All right, last time we also talked about, introduced in a superficial way, acyl substitution under basic conditions. And this is a little bit or a lot more complicated. Once again, you're looking for the carbonyl compound, where the carbonyl carbon is bonded to something that's not carbon and not hydrogen. And now the nucleophile is going to come in because it's basic conditions, you're going to be looking for a base. So what you're really going to be looking for is something with an O minus, a C minus, an H minus, or an N minus, for example. Okay, so with hydroxide ion, well, instead of that, that's my concrete example. Let's keep everything really general at the beginning here. So there's the nucleophile. Its nucleophilic atom is coming in with a negative charge, basic conditions. And once again, the thing that's not carbon and not hydrogen is going to go away, and the nucleophile is going to take its place. And because one of the things we believe in is charge conservation, since this is neutral and this is negative, the product has to have a negative charge. And so the leaving group leaves with this Z minus, as Z minus. Okay, so that's acyl substitution basic conditions, but the issue with acyl substitution under basic conditions is that these guys, is that this thing here may continue to react, may keep on reacting. And it's not all, the acyl substitution is over, but the reaction isn't over because the product of the acyl substitution frequently may engage in another kind of reaction, which is not acyl substitution. Okay, and so a good example, a concrete example of this would be if, say, we took an ester, all right, and now the nucleophile here would be OH minus. The thing that's not carbon and not hydrogen is going to break off. The nucleophile will take its place. And so that OCH3 went away. The nucleophile OH minus took its place, and that leaving group OCH3 came out with that negative charge. The acyl substitution is over, but the reaction is not over. And so this is what I mean when I say that in acyl substitution basic conditions, the product of the acyl substitution many times engages in a second reaction that is not an acyl substitution reaction. And here in this example, we see that's a carboxylic acid, that's a base. How do I know it's a base? Because there is an O in Chun, and I see that negatively charged oxygen. That's an acid, that's a base. These guys do an acid-base reaction in which they swap a proton. And so the acyl substitution reaction ended, but the reaction, it didn't end. And these would be the final products. There's a swap of a proton between the carboxylic acid and the base to produce this carboxylate and methanol. So if you just, if all you do is kick out the thing that's not carbon and not hydrogen from the acyl carbonyl and slam in the nucleophile, if it's basic conditions, you're probably going to make a mistake, because the product of acyl substitution under basic conditions keep reacting. Now, if I wanted the carboxylic acid, here, what I would have to do is have a totally separate workup step where all I'm doing is replacing the, all I'm doing now is protonating that O minus with this proton. Okay, so acyl substitution basic conditions, a little bit more complicated than acyl substitution under acidic conditions. All right, so in our introduction last time to acyl substitution, those are the issues that we raised. Now, how about let's talk about mechanism. Okay, so I have a concrete problem for us here. Let's write the mechanism for this reaction. Okay, there's our starting material. Acidic conditions. the product is that plus water. Okay, so let's write a mechanism. One of the things that we've said quite a lot is that anytime we see a carbonyl compound sitting around in acid conditions, usually the first thing that always happens mechanistically is what? Protonation of the carbonyl oxygen, followed immediately by attack on the carbonyl carbon by the nucleophile. So, you know, that saying that we repeat so frequently, we can take that to the bank again, because there's a carbonyl compound. It happens to be an acyl derivative. There's the acidic conditions. The first step in our mechanism is going to be the protonation of the carbonyl oxygen by the acid. So first step is protonation of the carbonyl oxygen to give this intermediate. And this oxygen has to have a positive charge on it, protonation of the carbonyl oxygen. And then the second step that we encounter oh so frequently, so many times, is the attack on the carbonyl carbon by the nucleophile. And in this case, the nucleophile is this guy, this oxygen atom down here. Attacks the carbonyl carbon, and then this double bond collapses. The oxygen atom eats up the electrons there. And so we have an intermediate, our next intermediate is going to have OH over here. That OH that was originally present is still there. And the nucleophilic oxygen atom came in. And notice that that this oxygen here has a positive charge on it because we're under acidic conditions. And so when we run a reaction in acid, there is no O minus, H minus, N minus anywhere, right? None of those strong bases can exist in acidic conditions. So this proton doesn't fall off, then oxygen attacks. Because if this proton were to fall off, we would get O minus. What I'm trying to say is that this OH group attacks intact with that proton still there. Okay, and so now, so those are our first steps. We encounter these steps over and over and over again. Protonate the carbonyl oxygen, attack the carbonyl carbon with a nucleophile, and now we have a lot of fiddling and diddling with protons. So instead of rewriting all of those structures, I'm just going to use this symbol here, meaning a protonation, deprotonation sequence. So some base comes along, removes the proton from the positively charged oxygen. That proton goes off into the solution. It's never heard from again. But there are a lot of other protons in the solution. One of them is going to pop on one of these OH groups up here. So that plus minus H plus means take a proton away from somewhere, bring a proton back somewhere else in the molecule. Okay, so in our mechanism, we see we need to produce water as a product. So the deprotonation of this oxygen and reprotonation on this other oxygen up here, that has manufactured an oxonium ion, an oxygen with a positive charge on it. And we said that whenever we see these positively charged oxygens, they're going to do one of two things. One of them is undergo deprotonation, which this thing is not going to do because it just picked up a proton, or it's going to function as a leaving group. So that's exactly what this thing does. We need to explain how water is formed. So OH plus goes away. So we're going to try to continue and conclude up here. So water goes away and we have this intermediate now. Let me rewrite this to show what happens next more explicitly. Okay, so we've made this thing that kind of looks like a carbocation. That's exactly what it is. It's resonance stabilized by the oxygen up at 12 o'clock and at 3 o'clock. So this is quite a stabilized carbocation. The reaction is catalyzed by a proton. A proton got the reaction going in the first step, and now the last step of the reaction mechanism is going to be the removal, the deprotonation of that oxygen atom to arrive at our final product. Okay, so that would be the mechanism for this acyl substitution. A couple of things about this mechanism that you want to note is, again, the first two steps, they're just, canonical. They just happen so frequently. Protonate the carbonyl oxygen, attack the carbonyl carbon with a nucleophile. Then there's fiddling and diddling with protons, and finally expulsion of a leaving group, and then a final deprotonation. So mechanism's not too bad. We've seen this kind of chemistry before. All right, so that was an example of writing a mechanism, acyl substitution, basic conditions. Acidic conditions. All right, so now let's try writing a mechanism of acyl substitution in base, under basic conditions. And so here we're going to do the steps of acyl substitution, and then we have to wonder, does that acyl substitution product, does it keep reacting, and what on earth could that second reaction be? Okay, so there's our acyl derivative, going to make it an ester, and it's going to react with the Grignard, a Grignard reagent. So maybe let's put, can put phenyl magnesium bromide. And for reasons that you'll see in a minute, let this be present in excess. That will be step one. Step two, after we do a Grignard reaction, we nearly always have a workup with aqueous acid. And so it would be nice if what happened here is OCH3 went away and the nucleophile, which would be pH, would take its place, but that's not what happens. Our final product here is going to be this, an alcohol, right, which is not an acyl derivative. And notice that what used to be the acyl carbonyl, this guy here, I'm putting a dot on him, has now turned into an alcoholic carbon. So this reaction is a lot more involved than just kicking the leaving group out, kicking the thing that's not carbon and not hydrogen out, and putting the nucleophile in its place. So let's write a mechanism for this reaction. All right, so remember phenyl magnesium bromide. This reacts as if it were pH minus MgBr plus, right? Okay, so our first step in the mechanism here would be the pH minus MgBr plus. The acyl carbonyl is an electrophile. That's a nucleophile. Remember, this represents a carbon atom with a negative charge on it. So we know we're under basic conditions. So the nucleophile attacks the carbonyl carbon. And we could picture MgBr plus swimming around in the solution momentarily. And so we get this intermediate here. And now, if it were just a acyl substitution under acidic conditions, we would slam this negative charge down and kick out the leaving group, but that is not going to be what happens. Next, we see, oh, this MgBr plus, that's going to coordinate with that oxygen. And so we get this, oh my God, stuff up here. All right. Okay, so now the nucleophile is in. Now the leaving group, the thing that's not carbon and not hydrogen, goes away. So that functions as a leaving group. And we get that plus C. Okay, I don't need this guy anymore. I don't need this guy anymore, so I'm just going to write him underneath the arrow here. Okay, so what I need is this. And we got CH3O minus coordinated with MgBr plus. Okay, so that's like the organic junk we don't care about. So that's the acyl substitution part of the piece. The carbonyl carbon bonded to something that's not carbon, not hydrogen, was attacked by a nucleophile. The thing that's not carbon, not hydrogen went away as a leaving group, and the nucleophile took its place. But as we said already, the acyl substitution comes to an end, but the reaction does not come to an end, because this is a ketone. This is a Grignard reagent. And we know that Grignard reagents react with ketones. So this guy, maybe put him in brackets to show that he is not going to be around for very long, because now he is going to undergo a reaction which is not acyl substitution, because there's a carbonyl carbon, but he's not bonded to something that's not carbon and not hydrogen. He's bonded to carbon on the left and carbon on the right. So he's not an acyl derivative, and the thing that happens next is not an acyl substitution. It's the reaction of an aldehyde or a ketone. It's addition. So we had excess phenyl magnesium bromide, right? And so now we're talking about the follow-up reaction. The acyl substitution is over, the reaction is not over. A lot of arrows going on there, just mostly to save time. And so we get this thing where that what used to be the acyl derivative has added a second equivalent of Grignard reagent. And over here we have OMG BR plus. We have this thing, BR plus. Okay, now the reaction is over. That is the product of step one of this in this reaction mechanism. Okay, now acid workup just liberates the H3O plus, that just liberates the alcohol. It replaces the MgBr plus with a proton, and the inorganic junk we don't care about would be that MgBr plus still sticking together, but now it is ionically associated with the hydroxide ion. Okay, so here's an example of acyl substitution basic conditions. And once again, just to belabor the point, it's an acyl substitution, and then there's a follow-up reaction which is not an acyl substitution. Okay. So how about let's try this problem. more acyl substitution basic conditions. What we're really looking for is what is that follow-up reaction. So what if I were to take, let's take an ester. Let's take this ethyl ester. And this time, let's react it first step with lithium aluminum hydride. Is that a base? Oh my heavens, yes. Because remember, lithium aluminum hydride reacts as if it were H minus, right? And H minus is one of these strongly basic species. And then we have an acid, an aqueous workup. Okay, so let me give you a minute. Let's try to predict the product. You get an acyl substitution. Look at the product of acyl substitution. Is that the end of the story, or does that continue to react? Any questions about anything? I think you can unmute yourself. Does anyone have any questions for me about anything?
I have a question about test 2.
Okay. I don't know if I know a whole lot about it, but shoot.
Yeah, do you think these like acyl stuff will be on it, or will it just end?
No, I'm talking about acyl substitution because we can't burn 4 weeks talking about exam 2. On Friday at my discussion, I'll go back to exam 2 and I'll have a review of exam 2 then. But I can't just, coronavirus or exam 2, whatever, life goes on for a lot of us.
Thank you.
Okay, sorry if that's not the answer you wanted.
It's good.
Anybody have any other questions about anything? I think you can unmute yourself. So are you giving it a shot? Hope so. All right, so I'm just going to present a mechanism for this, but as a simplified mechanism, which is just illustrating the most important intermediates and the most important processes. Okay, lithium aluminum hydride, the tetrahydroaluminate ion. So there's its structure. Remember, this acts as if it were H minus. The H pulls out of the aluminum, attacks the carbonyl. Can't stop there, because if I stop there, I'm going to have a carbon with 5 bonds. And so I get AlH3 swimming around in the reaction mixture. All right, so get something that looks like that, right? The nucleophile has attacked the carbonyl carbon. And now what's the next step? Expulsion of the group that is not carbon and not hydrogen. So we slam this electron pair down and kick off the leaving group. And so I have this plus O minus, right? That's the leaving group that went away. But what we see here is the acyl substitution is over, but the reaction isn't over, because this is an aldehyde, and aldehydes also react with lithium aluminum hydride. Notice that I didn't write excess lithium aluminum hydride the way I did in the previous problem. I wrote excess Grignard reagent. I didn't write excess lithium aluminum hydride here. Why not? Because lithium aluminum hydride has 4 hydrides. So 1 mole of LAH can take care of quite a few moles of ester. It actually will be 2. So we don't need excess lithium aluminum hydride, because the lithium aluminum hydride can continue to transfer more hydride. See, so like maybe this guy could get together with this one. This one could get together with this one. Aluminum has this empty orbital on it, which could be attacked by the oxygen. And so I get something that looks like, this. See, and that's not lithium aluminum hydride, but it reacts like it were lithium aluminum hydride. Get rid of this ethoxy group and put an H there. Well, that's LAH. So this guy is a hydride transfer reagent, just like LAH, the original LAH was. So that's why I'm trying to explain why I don't need an excess of lithium aluminum hydride. 1 mole of lithium aluminum hydride is enough to take care of 4 moles of ester. Okay, back to this. The acyl substitution is over. The reaction isn't over. That's an aldehyde. And aldehydes also undergo these these hydride transfer reactions. So this guy is going to come in here, transfer a hydride to the aldehyde carbon, and we end up with this. And this O- is ionically associated with the lithium ion, which has been just a spectator everywhere. Okay, now step 1 is over. Right, there's no more carbonyl, there's no more nothing left that can react with lithium aluminum hydride. So now this waits around for workup, and now when we add water, that's going to replace, you could add water, you could add OH-, you could add H+, so some kind of aqueous workup, and that is going to replace the lithium ion replace Li plus with H plus, and there's our final product. So again, this is another example of acyl substitution comes to an end, but the reaction doesn't come to an end because the product of acyl substitution under these reaction conditions can continue to react. Okay, so I'm going to shift gears into something else. Are any questions about anything? No? Okay. All right, so acyl substitution, particularly under acidic conditions, pretty easy, right? You just whack off that leaving group and slam the nucleophile in its place. But now we have to start adding on the complications, because there is something that we have to watch out for, is that there is a definite order of reactivity among the acyl derivatives that leads to the observation that not every acyl substitution that you can write on a piece of paper is actually going to happen. Okay, there is a reactivity order. And let me write the order of reactivity and then make the executive statement about it. The most reactive acyl derivatives are the acyl halides, right? Where X is going to be Cl or Br or I. I guess it could be F, but it never really is. And then the next most reactive are the anhydrides. And so this is kind of a strange class of compounds that maybe we didn't meet in Orgo 1, or haven't talked about in Orgo 2, that's an anhydride. And now, just for completeness and correctness, right, the next most reactive is going to be the aldehyde. An aldehyde is not an acyl derivative, but if you have a molecule that has an acyl carbonyl and an aldehyde carbonyl as well, that aldehyde could also react, right? So this is where aldehydes are in reference to the other acyl derivatives. And then we have the ketones. Ketones are not acyl derivatives, but if you have a molecule that has an acyl carbonyl and an aldehyde or a ketone in it as well, and only 1 mole of nucleophile, then there's a crisis. Is the aldehyde or ketone going to react, or is the acyl derivative going to react? So I'm putting in the aldehyde and the ketone here just for reference. This is where aldehydes and ketones are in relation to the other acyl derivatives. Okay, next, the carboxylic acids and the esters are about equally reactive. They're about equally reactive. And then the next would be the amides, and then the least reactive acyl derivative are the carboxylates. So this kind of makes sense because this molecule has a negative charge, this carboxylate, it has a negative charge on it, and a nucleophile doesn't want it. A nucleophile has a lot of negatively charged electron density. There's no way that a nucleophile is going to want to get close to this carboxylate because negative hates negative. So this reactivity order, this entry here, makes some sense. Okay, and so now what is the explanation for this reactivity order? The explanation is the leaving group here. Oh, I better give myself more room than that. The leaving group here is X minus. The leaving group here is carboxylate. That's not an acyl derivative. That's not an acyl derivative. The leaving group here is alkoxide. The leaving group here is going to be an amide. And the leaving group here, well, don't really know what it is. O2 minus, maybe. This is the only thing that we really need to know about. So that's the leaving group. This is the conjugate, the pKa of the conjugate acid. So this is going to be HCl or HBr or HI or HF. This is anywhere from about -10 to +3. This is a carboxylic acid. pKa of the conjugate acid is 5. This could be water or alkoxide. Oh, you know what? I forgot to write OH minus. OH minus is the leaving group there, and RO minus is the leaving group there. This is about 16 to 17, something like that. pKa here is 35. Okay, so the reactivity order is explained by the fact that the best leaving groups are the weakest bases. And the weakest bases have the strongest conjugate acid. So this guy here, conjugate acid, this is going to be, this guy here, this is the strongest, this is the weakest conjugate acid. This is the strongest base, the worst leaving group. These guys up here, these are the weakest acids. Sorry, these are the weakest bases. The weakest bases, and these are the best leaving groups. So this reactivity order can be explained by examining the quality of the leaving group. So I would probably just memorize this because it's important to know this order of reactivity so that you don't make a mistake when you're doing a product prediction problem. Okay, so there's a definite order of reactivity among the acyl derivatives. So just to save time, I know I hated this when my professors in college did this, but I'm going to do it anyway. I'm just going to erase this and I'm going to keep this. So what I'm just summarizing here is the order of reactivity. It can be explained by the quality of the leaving group. The best leaving groups are the weakest bases. The weakest bases have the strongest conjugate acids. The worst leaving groups are the ones that are the strongest bases. They have the weakest acids. Okay, so what is the upshot of all of this? Why am I talking about this? Because this order of reactivity is telling us you can go down the reactivity ladder, comma, but can't go up the reactivity ladder. Okay, so in other words, that is saying that if you start with an acyl chloride, you can make an anhydride, you can make a carboxylic acid or an ester or an amide from an anhydride, from an acyl halide, but you can't make an acyl halide from an amide. You can't make an acyl halide from an ester. You can't go up this ladder, you can only go down. Of course, the truth is so messy. There are a few exceptions that I want to talk about, but not really many exceptions. Okay, so what do I mean by this? So something like this, acyl halide plus CH3OH. There's the carbonyl carbon bonded to something that's not carbon, not hydrogen. That's the leaving group. He's going to break off. The nucleophile will take its place. Let's say this is happening under acidic conditions. So the nucleophile took the place of the leaving group. We got HCl. That's okay because I'm going down the reactivity ladder. I'm going from way up here to down here. That's okay. But this is not okay. If I start with let's say an ester and react that with a carboxylic acid, right, where this oxygen is the nucleophile. There's the carbonyl carbon that's bonded to something that's not carbon, not hydrogen. Let's say acidic conditions, the thing that's not carbon and not hydrogen, that is going to break off, and the nucleophile minus a proton is going to take its place. See, this is not okay, right? Just because I have a carbonyl carbon that's bonded to something that's not carbon, not hydrogen, just because I have a nucleophile does not mean that the acyl substitution reaction will happen, because what I've done here is I've gone up the reactivity ladder. As soon as any of this guy forms, it's way up here. It's going to immediately react with this guy, which is a nucleophile. And so we're back to where we started. The reaction will be reversed. So this is an important thing to remember, is that we can go down the ladder, but we can't go up the ladder. We can't make an ester from an amide, right? We can't make acyl halide from an amide. We can go down the ladder, but not up. And again, the reason is the product of going up the ladder is something that is extremely reactive, that's going to immediately undergo an acyl substitution. Okay, so once again, let's erase this and let's talk about the exceptions. I guess there are three important exceptions to this principle here. Exceptions. Three important exceptions. Okay, first is that if we take a carboxylic acid and react that with thionyl chloride, oh, we've seen this reaction a bazillion times, right? It's that Darzon's halogenation. The product here is going to be an acid chloride, right? The OH goes away and the Cl takes its place. So this is, we can go up the ladder from a carboxylic acid to an acyl halide, but this is not acyl substitution in its classical sense, so it's not really an exception to our reactivity principle, because this is not Cl minus, right? I'm not taking, or this is not HCl, so this is not really acyl substitution, it's something else, but it looks like acyl substitution. It looks like a violation of this this reactivity principle. But that's a good thing, because if we start with a carboxylic acid, we can use this reaction to make it an acyl chloride, and we're on the top of the heap, and now everything is possible. Right now we can make all of these other acyl derivatives. Okay, I'll talk about that more either later today or maybe next time. Next exception is that because the carboxylic acids and the esters are about the same reactivity, they are freely interconvertible, but that happens in acid only. So I can take a carboxylic acid, react it with an alcohol, and I can make an ester. And water would be the other, the inorganic product here. Okay, so these are about the same reactivity. Oh, this happens only under acidic conditions. And conversely, I can take an ester, react that with water, instead of HOR, now HOH, under acidic conditions, and I'll get expulsion of the leaving group alcohol and make a carboxylic acid. So another exception to this reactivity ladder is that I can interconvert between a carboxylic acid and an ester freely, but that is only under acidic conditions. Okay, the third and final exception, and this is a reaction that is pretty important, is that we can go from an amide to a carboxylic acid, right? And once again, it looks like we're violating our reactivity ladder, right? We can go from an amide up one notch to a carboxylic acid. So that's another exception. But this reaction is very, very difficult to perform in the laboratory. So this needs something like 6 molar HCl, and you have to heat it for several hours, or 50% sodium hydroxide, and you have to heat that for several hours. So even though it's possible to go from an amide to a carboxylic acid, it's a tough reaction. This is the only reaction, only acyl substitution reaction of amides, the reaction with water. An amide doesn't react with alcohols or with any other nucleophile, just with water by an acyl substitution. Okay, so those are the 3 exceptions to this reactivity ladder. Okay, ready to do some problems using the reactivity ladder? You can go down, but you can't go up. All right. So what about something like this? Plus methanol, acidic conditions. Draw the structure of the product. Okay, so what we're seeing here is an application of our reactivity, acyl substitution reactivity ladder. This carbonyl here is acyl on the left and it's acyl on the right. The question is, the crisis is, what is going to break off? Is that nitrogen atom going to break off, or is this oxygen atom going to break off? Draw the structure of the product. This is acyl on the left and acyl on the right, but only one of those, only one of those leaving groups will leave. So what's going to leave, the nitrogen or the oxygen? Anyone want to give it a shot? What's going to leave, the oxygen or the nitrogen? Draw the structure of the product. You can unmute yourself if you want to answer. Anyone want to give it a shot?
Oxygen?
The oxygen is going to leave. Good, whoever said that. Because if you cover up this part of the molecule, you see, you cover up this part of the molecule, you see, that's an amide on this side. If you cover up the other part of the molecule, see, that's an ester on this side. The ester is more reactive than an amide. And we just said that the only acyl substitution that amides engage in is hydrolysis, reaction with water. The amide does not react with alcohols or any other kind of nucleophile by acyl substitution. So indeed, what's going to happen is that the bond to the ester is going to break off, and the nucleophile will take its place, minus a proton. So the nucleophile was this molecule of methanol. You see how the nucleophile has taken the place of the departing leaving group. But this oxygen atom left the carbonyl carbon. It did not leave the molecule because it's still tethered to the molecule by other bonds. So the product of this reaction would be that, where the ester broke off, but it's not a free swimming entity swimming around in the solution because it's still bonded to the molecule by these other bonds. So that would be the structure of the product there. So that's one situation where we can apply our reactivity ladder. Okay, so let's try another one. What about this synthesis problem? I want to go from this, amide to this ester. Okay, so now that's a synthesis problem. How would you do that? What would be the synthesis? Well, one thing that will not work will be taking this amide and reacting it with methanol under acidic or basic conditions and the thing that's not carbon and not hydrogen breaks off, and the nucleophile takes its place, and the leaving group leaves with that extra proton. This, oh gosh, this thing here, this is no good, because we're defying the reactivity ladder. We can't go from an amide to an ester, because that's going up the reactivity ladder. So that's no good. We have to be more cunning. So anyone have a suggestion? Anyone have a suggestion of how to accomplish this synthesis here? It's going to be 1, 2, 3 steps. What are they? Anyone
Amide
want
to carboxylic acid.
Pardon me?
An amide to a carboxylic acid,
Yeah.
and then to a halide,
Yeah.
and then to the ester.
Great. That's exactly how we would do something like this, where we have to observe that reactivity ladder. We know that the only acyl substitution reaction that amides engage in is hydrolysis, reaction with water. So I could take this, water, acid, heat, right? This is one of our exceptions to the reactivity ladder, that we can go from an amide to a carboxylic acid. Okay, and now once we're at this carboxylic acid, we can do a Darzens reaction. And this is great because this is going to take us to the top of the heap as far as reactivity is concerned. We've gone from the least reactive, or one of a very low reactivity acyl derivative, to the most reactive by using this cunning hydrolysis step. And now we're going from an acyl derivative, which is way up here, to an ester. Now we could add methanol under acidic or basic conditions. I'm just going to use acid. And so that would be our synthesis, right? So this is a synthesis that depends on appreciation of that reactivity ladder. Okay, so I'm planning to stop there. I'm wondering, does anyone have any questions about anything? Any questions about anything at all? No. Okay, well then I guess I'll see you on Friday, where we will be reviewing for the long-awaited exam. Until then.